Hi, now we are going to delve into application 2, linear programming in manufacturing. Setting a low-cost production schedule over a period of weeks or months is a difficult and important management problem in most plants. The production manager has to consider many factors: labor capacity, inventory and storage cost, space limitations, product demand, and labor relations. Because most companies produce more than one product, the scheduling process is often quite complex. Basically, the problem resembles the product mix model for each period in the future. The objective is either to maximize the profit from or to minimize the total cost, production plus inventory of carrying out the task. Production scheduling is amenable to solution by linear programming because it is a problem that must be solved on a regular basis. When the objective function and constraints for a firm are established, the inputs can easily be changed in each month to provide an updated schedule. The case that we are going to look at is Greenberg Motors. Greenberg Motors Incorporation manufactures two different electrical motors for sale under contract to Drexel Corporation, a well-known producer of small kitchen appliances. Its model GM3A is found in many Drexel food processors, and its model GM3B is used in the assembly of blenders. 3 times each year, the procurement officer at Drexel contacts Arwin Greenberg, the founder of Greenberg Motors, to place a monthly order for each of the coming 4 months. Drexel's demand for motors varies each month based on its own sales forecast, production capacity, and financial position. Greenberg has just received a January to April order and must begin his own 4 months production plan. The demand for motors is shown in this table. For January, GM3A, 800 of them, GM3B, 1000, February, March, April, and so forth. Now, here are factors to consider for Greenberg Motors. First, the company must meet the demand for each of the 2 products in each of the 4 months. Also, the company would like to have 450 units of the GM3A and 300 units of the GM3B in inventory at the end of April, as demand in May is expected to be somewhat higher than demand in the previous months. Second, there is a carrying or holding cost for any inventory left at the end of the month. The producing too many extra units of either product may not be desirable because it causes some cost. The carrying cost assigned to the GM3A is 36 cents per unit per month, while the carrying cost for the GM3B is 26 cents per unit per month. Third, the company has been able to maintain a no layoff policy, and it would like to continue with this. This is easier if the labor hours used do not fluctuate too much from month to month. Maintaining a production schedule that would require from 2,240 to 2,560 labor hours per month is desired. So there's a fixed labor hours for this plant. The GM3A requires 1.3 labor hours per unit, while the GM3B requires only 0.9 labor hour. Warehouse limitation is the last one to consider. Cannot be exceeded without great additional cost. There is room at the end of the month for only 3,300 units of the GM3A and GM3B combined. So there is a limited space in warehouse, and they cannot carry more than 3,300 units of inventory at all at a given time. So these are the factors to consider. And 2 more factors to consider here. production costs are currently $20 per unit for GM3A and $15 per unit for the GM3B. And the cost will increase by 10% on March. That's another thing to consider. Lastly, in formulating this linear program, it is important to understand how all the important factors are related, how the costs are calculated, how the labor hours per month are calculated, and how demand is met with both production and inventory on hand. To help with understanding this, try to determine the number of labor hours used, the number of units left in inventory at the end of each month for each product, and the total cost. So you have to understand the relationship between inventories and inventory carrying costs and spaces so that we can properly schedule this production. So now let us define the variable first. We have AI, BI, and IAI and IBI. AI stands for the number of model GM3A motors produced in month. So this is the number of production of model GM3A, and I stands for period. Say January is number 1, and February is number 2, March is number 3, and April is number 4. If we had a 12 month, then 5, 6 to 12 we can go. In this case, we'll stop between 1 to 4 because that's the given demand we have. BI is number of model GM3B motors produced in a month. And IAI is units of GM3A left in inventory at the end of month I. In other words, if it is IA1, it means the remaining inventory for GM3A in January, at the end of January. If it is IA2, the remaining inventory of GM3A at the end of February. So that's what it means by IAI. And the same goes with IBI. That's remaining inventory for GM3B. I think this is a typo here. GM3B, not GM3A. And formulate objectives. The second step that we have to do, once you define these variables that you are going to be using, then we have to now define the objectives. And our objective is to minimize the total cost that incurs during our production in production schedule. So we want to minimize this production cost plus inventory carrying cost. So those are going to be combined together, and we are going to calculate that. So we have two parts in this total cost. The first one is production cost, and the second one is carrying cost. And production cost can be defined as 20A1. Why is it 20A1, right? So if you look at this table, GM3A, the production cost for GM3A is $20 from January and February. So we are going to use 20 times the number of production for A1. That's the cost for production of A1 in January. And A2 is 20 times A2, the number of production of GM3A in February. And that's the production cost of that time. And then we see that labor costs will increase 10% from March 1st. So 10% of production cost is $22. So from March, it's not just 20 times A3, but 22 times A3 because 10% of labor cost increased at the time. And then the same thing in April, 22 times A4. This is going to be production cost for GM3A motor. And then for GM3B, we have B1, and we know that the production cost is $15 for January and February. So 15 times B1 plus 15 times B2. And then 10% of increase, that's $1.50. So $16.5. If you add $1.50 to $15, then you get $16.5 times B3, the production of GM3B at March. And the same thing, 16.5 times B4, that's a production of GM3B in April. So this is going to be your cost of production for these two motors. And we have also inventory carrying cost, right? Inventory carrying cost. And we learned that it's 36 cents per unit per month. That's what we learned from the information given. So 36 cents we are going to be using. So 36 cents times A1. So the production of GM3A in January and in March, in February, in March, and in April. So that's inventory carrying cost for a GM3A, and then 26 cents for GM3B. And so what happens is we multiply 0.26 times B1. So the production in January and February, March, and April, then you have inventory carrying costs. So if you combine this together, then this is your objective, minimize cost. So 20A1 plus and so forth, plus, and this inventory cost, 0.36A1, 0.36A2, and so forth, and 0.36 IB4, because IB4, I'm sorry, I forgot mentioning, it's not B4, IB4, meaning remaining inventory of GM3A and GM3B, right? So it's inventory carrying cost. It's not number of production, but number of remaining inventory at the end of the month. So that's the inventory carrying cost. So we formulate the objectives. The next step is we have to formulate the constraints. And we realize that there are many constraints to consider in this case, in contrast to the relatively simple case of the portfolio selection. We see that 4 demand constraints, 1 constraint for each of 4 months for GM3A, and 4 demand constraints for GM3B, 2 constraints for inventory, the remaining inventory at the end of April, there was a requirement for that, and then 4 constraints for minimum labor hours, 1 constraint for each month, and the 4 constraints for maximum labor hours, 1 constraint for each month, and 4 constraints for inventory storage capacity each month. So in total, 22 constraints we have. So a large number of constraints we have, and linear program can handle hundreds of constraints. So that's why it is so powerful, and it's being used in many areas in business and in real life. And we also see that this information we can garner from the information given, and the labor hours has to range from 2,240 to 2,560. Warehouse limitation, the capacity is limited to 3,300 units. Labor costs increase at 10% by March 1. So that's what we need to consider. So then let's put first the demand constraints. If you look at the demand, it's 800, 1,000, 700, 1,200, and so forth. And look at this relationship here. So sales to Drexel this month is actually inventory at the end of the month plus current month production minus inventory at the end of the month. So if you use this relationship, then you can define the relationship between the current and the existing inventory and sale and current production. That will be the same with the sales to Drexel this month. So this number, for example, 800 in January, has to be equal to current month production, which is A1. That's a current month of production. And the remaining inventory at the end of the month, that's IA1, right? So A1 minus IA1 is going to be 800. We don't have inventory at the end of this month because it was the starting month, and we assumed that there was none. So it's 0. So 0 plus A1 minus IA1 equals 800. This is one constraint that we can find. The second one, 700. now we have IA1, which is the inventory at the end of this month, right? Plus A2, current month production, minus IA2, which is inventory at the end of this month, right? This month, previous month and this month, and that relationship exists, and that has to be 700. And in the same way, 1000 and 1100 is defined for A1 and IA1. This relationship has been defined. And the same relationship applies to GM3B, right? So current month production is B1, and the inventory at the end of this month is IB1. If you subtract that from B1, it has to be 1000, which is the demand of January for GM3B. And if you apply the same logic, then you have IB1 plus B2 minus IB2 is 1200, and so forth. This four relationship is going to be defined there. And we learned that at the end of the month, we have to have, at the end of April actually, we have to have 450. So IA4, which is the remaining inventory for GM3A, has to be 450, and IB4 is 300. So that relationship can be defined there. So we have how many? 10 constraints that pertains to demand constraints have been defined. And then we can define labor hour constraints. That's simpler than demand constraints. We know that our labor hours has to range from 2,240 to 2,560. So the production, and if you read the description carefully, you learn that it requires 1.3 labor hour to produce GM3A, while 0.9 hours for GM3B. And if you use this number, 1.3 times A1, the production number of GM3A, plus 0.9 times B1, GM3B at January, this has to be greater or equal to 2,240. However, it has to be less than 2,560, right? So it has to be greater or equal to 2,240, but less than equal to 2,560. In the same way, if you look at February labor constraints, it has to be greater than 2,244, but less than 2,560 hours. So we can create 8 labor constraints easily because of these constraints. Now, the third thing is storage capacity. We learned that maximum total inventory space available is 3,300 units, and therefore, at all time, the carrying number of inventory should be less than or equal to 3,300. Therefore, we can, put this equation there, IA1. So the remaining inventory for GMA3 plus, and the remaining inventory for GM3B has to be less than equal to 3,300. And that's for storage capacity in January. And you can do the same for the rest. And you can get 4 more capacity constraints right here. So then you have found all the constraints, and it's a matter of putting them into Excel, just as I have done before in the application of portfolio selection. So first thing that you want to do is you want to put all these variable names there, and then you will have to highlight this row as changing variables, and then the coefficient of them is right there, and then you have to put the equation into here, right? And then the maximum function or minimization function, in this case minimizing the total cost, so minimization will have to go in here. And then you have to just put all these coefficients for the first constraint, second constraint. So this is demand constraint. The first 10 constraints are the demand constraints, and you have to put those coefficient there, and the left hand side and right hand side and the sign you put in there, and then you move to labor hour constraints, and then you put those 8 of them you put in there, and then labor left hand side information and right hand side information, and the sign there. And lastly, we have capacity for constraints, 4 more constraints over there, and we put them there, and we formulate the Excel solver. You just execute that, then you have this result right here, production schedule, January, February, March, and February, and you will be able to find A1 is 1,277, and A2 is 223, A3 is 1,758, and A4 is 792, and B1 1000, B2 2522, B3 78, B4 1700, and A1 is 477. The remaining balance inventory has to be 477. For February, you should not have any, and for March 758, for April 450, and IB1 0 1322, and IB3 0, IB4 300, and labor hour required is 2,560, 2,560, 2,355, 2,560. So it ranges from 2,355 to 2,560 depending on the demand. And the total cost over here is $169,295 for this production scheduling. And we had 16 variables and 22 constraints in total, and Excel solver handled it for you. So this is how you can do this production scheduling. It's more complicated, however, it's no problem as long as we know what we are doing, how many variables we are handling, how many constraints we have. So it's a matter of formulating this problem and finding these constraints, and that's tricky. But once we figure that out, running it is not that difficult at all. And I encourage you also to look at the sensitivity analysis and see what kind of decisions you can make out of the result by taking a look at the sensitivity analysis.